In other words, the rate of the forward reaction, so it's the rate of forward reaction, is equal to the rate of the reverse reaction. This means, so if you have two reactions, like your products and your reactants, when the products are over here, and your reactants, they are going back and forth, and equilibrium is when they're in the middle, where if you added more reactants, more products would form. If you added more products, more reactants would form. Okay? And the way that we have this is we have a constant, K, in this case, K of EQ, K of EQ, equals the products over the reactants. So the concentration of the products to whatever their coefficient is over the concentration of the reactants and whatever their coefficient is. Another way of thinking about this is if you're on a treadmill and the treadmill is moving backwards this way. Say it's moving 3 miles per hour. If you're on the treadmill and you're walking forwards at 3 miles per hour, you're not going to be moving anywhere. You're going to be staying still. The treadmill will be moving backwards as you're moving forwards. If you up the speed of the treadmill to 4 miles per hour, and you're still going 3 miles per hour, then you're going to be moving reverse, or as related to this, more reactants will be formed. Likewise, if you were moving at 4 miles per hour and the treadmill was moving at 3 miles per hour, at 4, then you would be moving this way more, and more products would be formed rather than reactants.
You may not know this, but equilibrium occurs every day in our bodies. Hemoglobin, a protein responsible for transferring oxygen throughout the body by changes in the chemical equilibrium in the following reaction. So here you see hemoglobin. It's quite long, so I'm not going to rewrite it a bunch of times. So there's the chemical equation. And here I drew a little diagram because hemoglobin has to be able to pick up and drop off the oxygen throughout different parts of our body, and he does this through equilibrium. Okay, solubility is the ability for one substance to dissolve in the other. So here we have some salt, NaCl, which is the solute, and then here we just have H2O, water, which is the solvent. And we got some salt, we're pouring it in there. It's the ability for the salt to dissolve. And when talking equilibrium, the constant for this is K, solubility product, which is KSP. Okay. So molar solubility is the number of moles of the solute that fully dissolved in the solvent over the total number of liters present. And the way to solve for molar solubility is, for example, if you're given the following equation, AB2 solid goes to A aqueous plus 2B aqueous, and you're given your KSP, then you can just simply write your equilibrium expression. Since AB2 is a solid, it's not included in the expression, so I'm just going to go ahead. And then you just replace those for x's. So I'm going to give you x and then 2x squared. Which will give you x to the 4x squared, which will then in turn give you 4x cubed, and then you just plug in your KSP value and then solve for x, and that will give you the molar solubility.
So common ion effect is very important. I'll give you an example before I kind of explain it to you. Say we have BaOH, barium hydroxide, and it is normally insoluble. It's only very little solubility, and it creates barium plus 2, which is aqueous, and 2OH minus, it's also aqueous. So common ion effect says if you have two solutions mixed together, and the second one, they both share a common ion, such as in this case, if barium hydroxide was in a basic solution, that is pH greater than 7, it would have a content of OH minus, which is also present here. So if we had it in both, it'd be a common ion, as stated quite frankly in the title. And it would be like adding more products into this. So as we learned earlier, more products equals equilibrium shifted to the left. So in this case, if we had this, less products would be formed. So less OH minus and less Ba plus 2, and an increased amount of barium hydroxide, or in other words, the common ion effect reduces solubility. A saturated solution is a solution where there's very high concentration of solute. For example, at equilibrium, if you were to add more solute into it, it would no longer mix together. It would simply just collect at the bottom. So an example of saturated solution could be bath salt in water. If we add some bath salt, which starts out with a little bit, and mix it in, you will see the solution will start to change colors, and the bath salt will dissolve into the solution. As we add more, you can see the solution gets darker as more is being dissolved in. And then the more we add, it gets even more concentrated or more saturated. And then if we add a whole bunch, you see it gets very saturated. So we can tell now that it's reached equilibrium, because no matter how much more we add, it just settles at the bottom.
Alright, endothermic reactions. So first, we're going to start with endo. And in an endothermic reaction, energy is gained. So I'm going to do energy plus, and an exothermic energy is lost. And then, in endothermic, the delta H is positive. Exothermic delta H is negative. In an endothermic reaction, the heat, if you're adding heat, it acts as a reactant. So it goes on the reactant side. And then an exothermic heat acts as the product, so it goes on the product side. Thus making the equilibrium shift to the right. And with exo, the equilibrium shifts to the left. And then here we have an example of an endothermic reaction. It's ice melting, and the heat is being gained, and the ice is melting.
So heat plays a major role in solubility. If you increase the heat, a solid and a liquid will be more soluble. We set up an example to show you this. We have two M&Ms, same color, and 2 glasses of water. One's a lot warmer than the other one. This one's room temperature, this one we heat up in the microwave. Let's watch what happens when they both go at the same time. If you can tell, this one is forming bubbles because the candy coating on the outside is already beginning to dissolve. You can see the blue cloud forming below it and bubbles being released. And you can see the same thing on the other side, but it's happening much slower. This one's a much more violent reaction, and it looks like as if the shell is already being peeled away and floating to the surface. If we watch this one, the similar thing happens, just much more slowly, and it shows that the heat causes it to be more soluble. The Chatelier's principle was shown in our experiment because it was an endothermic reaction, which means that heat was serving as a reactant. Since we added heat, more reactants were present, which pushed the reaction to the right to compensate, such due to Chatelier's principle.